Can you?
It's great to be here, to be able to talk to you about electromagnetic signatures for massive black hole binaries. And we'll start with a fairly general slide. All of you know this, but black hole binaries are interesting because they are expected to be the most luminous sources of gravitational waves in the universe. And this will allow for us to study not only the black hole binaries themselves, but it will also allow us to put some constraints on cosmological parameters. But the ideal scenario, of course, for us is the situation where we can observe both electromagnetic and gravitational wave signatures from the same source around the same time. In this case, electromagnetic signatures will help us pinpoint position of the object in the sky because, as you know, LISA is not a pointed instrument, it's a all-sky survey. So electromagnetic signature can help us to pinpoint position of the object in the sky with a much greater accuracy. And it will also allow us to determine the redshift of the object, which will help break the mass redshift degeneracy. And even going further, and not considering only LISA binaries, but considering more massive binaries, this will allow us to study the parent population of objects and understand the population of massive black binaries as a whole, and put constraints on rates of detection for gravitational wave experiments. But it turns out that massive black hole binaries are hard to find, and practical difficulty arises from the need for high spatial resolution in order to detect binaries. And for example, the separation of orbital separation of 1 parsec at a distance of 100 megaparsecs translates into only 2 milliarc seconds of angular separation of the sky. And with spatial resolutions achievable today, it is much easier to spot a result of wide binaries or wide black hole pairs, such as NGC 6240, which was confirmed to have 2 active galactic nuclei at a separation of about 1 kiloparsec. Another interesting case is a radio-loud galaxy 0402, which was shown to have 2 compact cores at its center with separation of only 7 parsecs. The most likely explanation for the system is that it is a supermassive black hole binary, but except for the direct imaging, the second most appealing argument for presence of a supermassive black hole binary at the center of a galaxy is periodic manifestation of Keplerian motion. And an example for that kind of an object is OJ287, which is a blazar and which shows 12-year or nearly 12-year periodicity in its optical light curve. But even with these candidates and with a few more that we are aware of, currently we do not have a sample based on which we can piece together a binary evolution, and especially at parsec and sub-parsec scales. However, historically, lack of observational evidence has never been a problem for theory. Jokes on the side, it turns out that hydrodynamical simulations are really an excellent tool to study evolution of a binary in the presence of stars, gas, and dark matter, as Lucio and Massimo told you about. There are several more goals and challenges to be met on the road down towards this goal, and there is a need to extend calculations all the way towards the gravitational wave regime. And this is going to be challenging because with decreasing orbital period of the binary, this kind of simulation becomes increasingly more computationally expensive. And also, both the accretion rates, which will infer observational signatures, and orbital evolution of supermassive black hole binary at sub-parsec scales are sensitive to assumed thermodynamic properties of the gas disk, and they're very sensitive to aging and feedback. And they can ultimately determine whether the picture at sub-parsec scales will look more like this, where there is still some gas inflow towards the small circum black hole accretion disk, and where there is some significant accretion rate onto the two black holes, or if the scenario will look more like this, more similar to a gas or merger or binary. But there is another interesting issue that I wanted to mention today, and that is evolution of orbital eccentricity at sub-parsec scales. As you heard from previous speakers, rotating binaries that orbit in the same sense as a gas in the disk tend to circularize down to orbital separation of 0.1 parsecs, while counter-rotating binaries don't. The simple explanation of this process is that a supermassive black hole at apocenter interacts with particles in the disk, and a supermassive black hole moves slower with respect to the particles in the disk, and therefore will be accelerated through these interactions. While at pericenter, the opposite thing happens, and a supermassive black hole is decelerated by particles interactions with gas in the disk. So the sum of these two effects, its acceleration at the apocenter and deceleration at the pericenter, leads to circularization. However, at lower separations, black hole binary is expected to evacuate this low density region, to evacuate the gas from this low density region. And it's been suggested by Armitage and Natarajan that resonant interaction of a binary in this kind of geometry with preferentially cold circumbinary disk can lead to an increase of the eccentricity. And you can see in the top right figure the eccentricity growth over about 200 orbits of a binary. And you can see that in case of a cold disk, the eccentricity starts off very low, almost zero, and increases to over 0.2. And notice that while their simulation stops after 200 orbits, the eccentricity growth does not saturate, therefore leaving room for even higher eccentricities. Armitage and Natarajan calculated that when such binaries enter a gravitational wave regime, they will circularize to some degree via emission of gravitational waves, but there will still be some residual eccentricity, which will be in the range of 0.01 to 0.1, and which is the eccentricity residue that should be observable by LISA. And they further proposed that if an eccentricity is detected, that we can use that to discriminate between evolution of black hole binaries in a predominantly gaseous background versus evolution of a binary in predominantly stellar background, because in this second case, it is expected that this residual eccentricity will be negligible. And except for gravitational wave signatures, presence of any eccentricity is of course very important for electromagnetic signatures, because the accretion rate is quasi-periodic if binary is eccentric. And this is not only true in case of supermassive black hole binaries, it's also true for any other kind of binaries. And it's been shown, for example, by Gunter and Clay for T-Tauri stars. And in this case, they model the equal mass binary with eccentricity of 0.47. And this is the accretion rate to the primary and secondary black hole T-Tauri star that they calculated, and they overplotted the orbital phase on the top of it just for illustration. So let's try to summarize all these results in the case of gas-poor and gas-rich merger and see what kind of electromagnetic signatures we may expect to see. Obviously, in this gas-poor situation, there is not a lot of gas prior to the coalescence to be accreted, so low accretion rates, low chance of observing these objects, probably accretion rates probably of order of less than 10% that this would have in the absence of a binary. However, after the coalescence, the gas will catch up with a rapid black hole on the viscous timescale and give rise to accretion power luminosity of 10 to the 43 or 10 to the 44. And this will happen after 7, Milosavljevic estimated after about 7 years times the redshift factor for 10 to the 6 mass black hole. The situation looks slightly more optimistic, at least in the pre-coalescence phase for gas-rich case, because fairly early before the coalescence, while binary separation is still several parsecs or so, the accretion from this small circular black hole disk can power a double HDR emission. And it can do that for up to 1 million years. And smaller separation, 100 parsec or so, if there is still gas for binary to accrete and interact with, one may expect X-ray luminosities of 10 to the 43 or 10 to the 44, which is observable at redshift about 2. Volumetric luminosities of 10 to the 45 for 10 to the 8 solar mass black hole. And for eccentric prograde binaries, one may expect to find a periodic variability in both volumetric light, which is light powered by accretion, and also by emission from gas, and in X-rays, and also in broad H-alpha emission line profiles. So, what then happens closer to coalescence, or right after it? It was shown, or it was suggested that heavy binaries may have a precursor accretion episode, just because they will sweep any gas that was trapped in the orbit of the binary, they will sweep it and accrete it on their way to gravitational wave in spiral in coalescence. While light binaries can be followed by an afterglow on a approximately viscous timescale similar to the gas-poor case. And with all this prediction in mind, I would like to tell you a few more things about simulations that a group of us has carried out. These are hydrodynamical simulations with somewhat modified code gadget, which uses tree-on body and smoothed particle hydrodynamics methods. And these simulations, two massive black holes were described with two orbiting massive particles at 100 parsec orbital separation. And the model that we started with is a fairly simple one. It's shown in this figure here, where simply the primary black hole is surrounded, which is the more massive black hole, surrounded by a gaseous disk, while the secondary is on an eccentric orbit, and it truncates the disk of the primary. And we didn't include an accretion disk around the secondary black hole, just for simplicity reasons. And you can think of this scenario as being the most similar to the scenario of gap formation. Gas heating and cooling and some proximate radiative transfer are coupled, and they affect gas dynamics and gas thermodynamics. And the gas is being heated by both shocks and accretion power luminosity from the 2 AGM, or the black holes. We use this approximate radiative transfer to model the X-ray and Pau Amaro-Seoane light curves and Pau Amaro-Seoane emission line profiles for a brief period of evolution. And of course, we would like to have it for a very long period of evolution, but this is a computationally expensive thing to do. Oh, very bad contrast. Okay, so this movie is actually a sequence of snapshots in case of a co-rotating binary. Binary is coplanar. It has same major axis of 3000 m, eccentricity of 0.7, initially period around 16 years, and masses of primary, secondary black hole, and a gas disk as lined up on the side. The timestamp in years shows the time since the beginning of the simulation. And here in the top left panel you can see the distribution of gas projected into an XY plane of the binary. The top right panel shows the variable Balmer alpha profiles, which I hope you can see. Bottom left panel shows logarithmic temperature as a function of radius, and particles are color-coded so that this panel can be also used as a color table. And the bottom right figure shows the Tamara Q parameter, the logarithmic Tamara Q parameter, which is commonly used to determine whether the disk is stable to gravitational collapse. And as you will see, this disk is, because it's very light with respect to the mass of the binary. And as you would expect, the hottest particles are the most stable ones, while the coolest particles, logarithmic temperature, are the least stable ones. And note the fairly variable Balmer alpha profiles during the course of this simulation. So because it's computationally expensive, we were able to follow it on just few orbital passages, but we were able to calculate accretion rates onto the primary and secondary black hole, which are shown in the red line and the blue dashed line. And the arrows on the top mark pericentric passages, times of pericentric passages of the binary. And we find that accretion-powered X-ray luminosity for this accretion rates is about 10 to the 43 or 10 to the 44, which is observable out of a redshift of about 2. For comparison, I wanted to show you also the, one more time, the optical light curve of OJ287, where these spikes appeared approximately 12 years, with 12 years periodicity. This is a sequence of H-alpha emission line profiles with a time step next to each emission line profile. As you just saw, they're very regular and variable. And these properties of H-alpha profiles can be used if the profiles can be observed as a screening criterion in looking for black hole binary candidates in archival data, such as Sloan Digital Sky Survey, for example. And if they're monitored on a longer time scale, variability in these profiles can constrain the period and mass ratio of the binary. And I also wanted to show you some observed unusual Balmer alpha emitters. There is a good number of unusual, actually, Balmer alpha emitters out there, and it doesn't mean that every object that has an unusual H-alpha line automatically hosts a binary at its center. But hopefully candidates can be selected in this way, and long-term monitoring can show whether they're indeed hosts to black hole binaries or not. So, how am I doing on time? 5. Excellent, thank you. Let's switch gears to runaway black holes now. So, is there really do we need to worry about runaway black holes? Are we going to encounter them somewhere on the road? It seems that runaway black holes are a ubiquitous prediction of numerical relativity, and this kind of phenomenon occurs as a consequence of gravitational rocket effect. because before the coalescence, gravitational waves carry some net linear momentum. The post-coalescence remnant black hole will recoil in the opposite direction. It will receive some natal kick. And it turns out that in certain alignments of black hole spin axis prior to the coalescence with orbital angular momentum, these kick velocities can be quite remarkable and can reach 4,000 kilometers per second. Now this is enough to kick the central supermassive black hole out of its host galaxies. So if this kind of high velocity recoils are common, one would expect to see many empty nest galaxies that don't carry a central supermassive black hole at its center. And numbers in this bullet suggest that high velocity kicks are really not all that uncommon. And basically to have a 1,000 kilometers per second kick, the probability is between 8 and 36%, where this range is actually, or lower and upper limit are from calculations of Schnittmann and Buonanno and Campanelli. And to have a kick higher than 500 kilometers per second, this can happen in 30 to 70% of situations where we're thinking about a major merger, meaning the mass ratio is higher than 1 to 4. And for some isotropic distribution of spins and spin magnitudes of 0.9. So, because this is not necessarily what we see, and we think that every galaxy with a bulge has a central supermassive black hole in it, these two things are in apparent contradiction with each other, and they prompted us to think of a mechanism which can prevent black hole ejection. And we proposed that in gas-rich mergers, gas storks suffice to align spins of supermassive black holes with their orbital axis and with a large-scale galactic disk. And in this configuration, it turns out the kick velocity is fairly low, so it doesn't really threaten a central supermassive black hole. And you can hear more about it in Carl Miller's talk. So, okay, there are reasons to think there are mechanisms which may prevent black hole ejections, but also you may think of a situation where one has a gas-poor merger scenario, and there are not enough gas stores to align spins, and high-velocity kicks can happen. So then the question is, can we see these runaway black holes? Several authors have suggested that yes, there may be observable signatures of runaway black holes, and the main idea is that runaway supermassive black hole can retain its inner disk, which will remain gravitationally bound to the recoiling black hole. And if the mass of the retained disk is about 20% of the mass of the black hole, and if that supermassive black hole accretes to nearly Eddington rate, this will be enough to power the AGN for about 10 to the 7 or 10 to the 8 years. And in that time, recoiling at the speed of 1,000 kilometers per second, this supermassive black hole will reach 10 kiloparsecs distance from the center of its host galaxy. So now that is a quite striking observational signature. An off-center AGN, especially at several kiloparsecs distance, would be a telling sign. There are also some other mechanisms which can produce observational signatures, and they've been suggested by Lipoi et al. And Shields and Wine. And these are transient shocks in the disk that occur after the black hole recoils. These authors predict that these shocks can lead to 0.1 to 10 Eddington luminosities, peaking in soft X-ray band, And this increase in luminosity or transients would trail after gravitational wave event on timescale months to year. And these two figures are just an illustration of geometry of the disk in case of kicking the plane of the galactic disk and keep orthogonal to the plane. And someone already thought of, okay, I'm finishing, sorry. Someone already thought of looking for this ejected supermassive black hole. Bonning et al. Had a very nice idea, and they basically looked for emission lines from this small disk that is gravitationally bound to a recoiling black hole, and thought that this should show a shift in velocity space from emission lines contributed by the large-scale gas disk. And they found no convincing evidence from 2600 SDSS objects. They found no convincing evidence for recoiling black holes. So this is my last slide, and attempt to inspire discussion. And this is what I think are some things that we should think about. And there is a need to extend calculations of binary evolution all the way to gravitational wave regime in order to determine whether viscous torques can deliver massive black hole binary all the way, or whether it will need some help from stars and massive perturbers and relaxation processes in order to merge. Also, how high can binary eccentricity be driven by certain binary disk? This is an important question which will have implications for both magnetic and gravitational wave signatures. I wanted to point out that very long baseline array recently achieved 10 microexact accuracy in spatial measurements, and it seems like it is well suited now for searching subparsec binaries. And for example, now it should be able to resolve binary OJ287, which, according to a model of Lactang Tonen, has orbital separation of only 0.056 parsec. And I think that in terms of angular separation, that's like 12 microseconds close. And related to the second part of the talk, to runaway black holes, really need better estimates from hydrodynamic simulations because exciting as they are, these results are still analytic, based on analytic arguments. So we really need to know what fraction of disk mass remains bound to supermassive black hole, and how much Asian feedback is there, what are the thermodynamic properties of this recoiling disk in order to figure out what fraction of luminosity is powered by accretion, shocks, and time scale. Thanks.